Today, we meet the Tesla of aircraft travel. Let's get into it.
From my obsession with aviation, have developed a new kind of supersonic propulsion system. It's very similar to existing jet engines, but making affordable supersonic flight.
You can simplify it all down to like four forces that are, all kind of acting against each other. And so I think the concept of paying off that mass debt is a really great way to look at it.
That is the long-term goal of replace airline travel with low-cost, supersonic, on-demand flight.
It totally radically changes, I think, like the operating model of the aircraft.
Well, welcome back to the Tech Optimist. This is a Meet the Startup episode for you today. And the startup today is Astro Mechanica. Now, on the AV side of the ball, who's on the mound? Our starting pitcher is Drew Wandzilak, senior associate here at Alumni Ventures. He's in pinstripes. And then behind the plate, or up to bat, I should say, is Ian Brooke, founder and CEO of Astro Mechanica. And then myself, my name is Sam. I am the guide, editor, and just, I take you through the episode each week. So a little bit about Astro Mechanica and a little bit about the conversation that's going to happen today. Now, Ian is a very experienced pilot and mechanical engineer. So he knows the ins and outs of airplanes like nobody does. Like this man's knowledge on airplanes and engineering is insane. Like you'll see it here in the interview. It's really cool. There's a lot of really nuanced sort of engineering and technology that they talk about today in the episode that really helps define what the new jet engine is, which is what Astro Mechanica is doing. So I want to read a little bit of a snippet from a tweet that Ian gave out in February of this year. My company, Astro Mechanica, has invented a new kind of jet engine. And like any existing engine, it's efficient at every speed. Because it's efficient at every speed, we can use it in a new way as the first stage of an orbital launch vehicle. The resulting platform will get payloads to orbit dramatically cheaper than all rocket systems, among many possible applications. So they're going to talk more about it here in a few minutes, but I'll stop yapping and let's get into it. Enjoy. As a reminder, the Tech Optimist podcast is for the informational purposes only. It is not personalized advice, and it is not an offer to buy or sell securities. For additional important details, please see the text description accompanying this episode.
And we'll start things off. Hello, everyone. I'm Drew Wandzilak. I'm an investor with Alumni Ventures, and I am here with Ian Brooke, who is the founder and CEO of Astro Mechanica. It's so great to have you on, Ian. Let's kick things off with just a brief introduction on yourself and the high level elevator pitch on Astro Mechanica and what you guys are doing.
Yeah. So hey, I'm Ian Brooke, founder of Astro Mechanica. So my quick bio on this, lifelong pilot. And so I use the term like full stack mechanical engineer. I do everything from, CAD to machining to, selling the products. At least this was sort of my prior work. So everything from atoms, from like the raw material to delivered products has like always been my thing. And have from my obsession with aviation, have developed a new kind of supersonic propulsion system. It's very similar to existing jet engines, but making affordable supersonic flight.
For those of you who are not aware, like I was not aware, supersonic flight refers to travel through the air at speeds faster than the speed of sound. So this is approximately 767 miles per hour or 1,234 kilometers per hour at sea level. This speed is also referred to as Mach 1, and speeds between Mach 1 and Mach 5 are considered supersonic, while speeds above Mach 5 are classified as hypersonic.
And I think the big unlock here is what you guys are describing as this turbo electric adaptive engine. And correct me if my phrasing is off, or there's obviously additional pieces to that. Explain the technology. I mean, what is it that you guys are building? How does it work? In as simplest terms as possible, and we can dive in a little bit deeper where it makes sense.
Yeah. So I think the way to think about it is, aircraft engines do two things, and we tend to think of it as one thing, but they do two things. There's a thermodynamic cycle, which is extracting energy from fuel to create power. And then the second thing is propulsion, or generating thrust from that power. And in all engines, these two things sort of happen at the same time, so they get a little conflated with each other. But what makes for good thermal efficiency and what makes for good propulsive efficiency are two very different things. And the insight that I had from some, obsessive work I was doing in aviation was electric motors had gotten extremely lightweight. And so that lets you do something very new, which is you can use an existing jet engine, turbine engine, turboshaft engine, turbine thermodynamic cycle to generate electrical power. It's now very light. The electric motor is the heavy piece of this previously. It wasn't viable. Now it's very lightweight. Now you can create a separate propulsive engine. So it's like taking that typical airplane engine and splitting it into two things. And now they can both be optimized for, what is optimal for them. So the turbine core gets to run at its sweet spot for max thermal efficiency. And then on the propulsive end, the one, actually pushing the plane through the air, that one can now sort of adapt. This is where the turbine and the adaptive cycle part, and they're electrically joined. This is where turboelectric adaptive engine comes about. But the adaptive side can now essentially behave. It can be the correct propulsive mode or cycle for any given speed that the airplane is at. So if you're subsonic, that looks kind of like an airliner. It's a fan cycle that works really well up to like Mach 0.8. Then when you go faster than that, you can become more of a jet cycle. You start to combust that air behind the fan, and which your perfect engine would ideally only push air out the back slightly faster than the airplane is going forward. Anything faster than what the plane is like. If you're going 250 meters per second, you don't want to be pushing air out the back at 500 meters per second. That's a lot of wasted energy. Instead, you'd rather move a large mass of air, say at 300 meters per second, when you're going 250. So it's doing that, and that becomes viable when you have this thing split. So yeah, this is in a nutshell, we have like a highly variable exhaust velocity that we can trade off with mass flow. So that's it in a nutshell. Hopefully not too technical, but.
Yeah, I think, emphasis on not too technical. I still think there was a lot of words in there for, non-aerospace engineers. We joked when we first met, I took some summer classes. So the terms I know, right? But I'm going to challenge you a little bit here because we talked about some of the difficulties of storytelling around deeply technical solutions. Like, let's do a little like aerospace engineering, 101, class number 1 with Ian. How does the jet engine that people kind of hear about or see about today, how does that work? And then maybe we can dive into the individual pieces. You touched on electric motors and how that's kind of changing the paradigm in jet engines. So in as quick and simple a way as you can, what is the science, what is the technology behind the existing state of a jet engine?
Yeah. So jet engines, as all like combustion engines, they do 4 things. We call it suck, squeeze, bang, blow. Sucks in air, it squeezes it, it explodes it, and it exhausts it out the back. That happens on all airplane engines. And so when you go on an airliner, I think we mostly use like gates now, but when you walk on an airplane, you see that big fan. That is driven from the actual, like that fan is the thing pushing the air, but that's being driven by a separate thing. And that separate thing is the one sort of running this thermal cycle, as we would say. That's the one burning the fuel, and that's pushing the fan. So, or spinning the fan, which pushes the plane. So that's a normal airplane engine. We're really just doing something quite like that, except we don't directly drive it. We take that core that spins the fan, we put it kind of next to it, and we electrically couple them. So that's and then when we do that, now we can burn fuel behind that fan in another way, and that's what allows us to go even faster. It's like a very efficient afterburner. So yeah, that hopefully this is slightly simpler, but
it is. I think it was tremendously helpful, and then even within that. I'll keep it simple, maybe losing some nuance, but in that kind of jet engine, the engines you see on the commercial airliner that you took on your last trip somewhere on a vacation looks very different than the engine that you would see with an afterburner on a fighter jet. Mm-hmm. Talk to the differences there, again, because the technology and conceptually very similar. Mm-hmm. What are those differences and kind of what are the trade-offs between something that is, maybe a little bit more high efficiency versus something that's a little bit higher, quote unquote performance or speed?
Yeah. So I guess it can be summarized as you're trying to create thrust. Thrust is mass times velocity. So it's how much air you're taking in, X amount of air, and you're pushing it at X speed. It doesn't matter from a thrust perspective whether you're doing 1 kilogram per second, 1 unit of air at 100 units of speed, or flip that. That is equal thrust. The difference though is, so we've described this. This is true if you're at 0 miles an hour, but as you start to move, well, you have some forward speed, and so the difference ends up being if you have a very low velocity, that becomes like exhaust velocity. That doesn't work when you're going really fast, and that's why fighter jet engines look different. Is like, well, they're pushing air very fast all the time. So when you're slow, that's wasted energy. But when you're fast, that's necessary. This is why like an airliner engine can't just go supersonic. The exhaust velocity would be too low. But it's really efficient because it's just taking in all of this air. Like air is around us. That is free reaction mass. It's free stuff to push out the back. And the reason you don't want to push air too fast is kinetic energy is 1/2 mv squared. So that v squared really penalizes you as opposed to just taking in more mass. So that's why this is a thing that you want to optimize around. And because in a normal engine, these things are like physically linked, you're just, whatever the size the engine is, you're just committed to that. I sort of have this analogy of like, it's a fixie bike. When you build a normal engine, it is committed to one ratio of this. You can't turn these knobs. For us, by decoupling them, it's like we've introduced a gearbox into this equation. So now we actually can vary these things.
All right, everyone knows the drill. We're going to take a break and then we'll be right back. Don't go anywhere.
Hey everyone, just taking a quick break so we can tell you about the U.S. Strategic Tech Fund from Alumni Ventures. AV is one of the only VC firms focused on making venture capital accessible to individual investors like you. In fact, AV is one of the most active and best performing VCs in the US, and we co-invest alongside renowned lead investors. With AV's US Strategic Tech Fund, you'd have access to an investment portfolio focused on technologies that are critical to bolstering US national security and economic prosperity. We prioritize 3 key areas: homeland security, cyber AI and digital strategy, and space innovation. By investing in companies innovating in these areas, you can support early stage ventures and help encourage sustained growth and technological progress in the United States. If you're interested in learning more, visit av.vc/funds/strategic tech.
And it's incredibly helpful. And the second question I always ask companies after, like, well, first, what are you doing, right? I think the second most important question is the why now piece. And you touched on this a little bit with, I think the performance and the cost and the availability of the electric motor. Mm-hmm. Dive into that a little bit more in terms of, why is it taken so long? I think as people learn about what you guys do, it's going to go, oh, okay, that makes a lot of sense. Why is it 2024 and we're just figuring this out now?
Yeah, I mean, there's a little bit of this is a second order effect of the EV revolution, I would say, is the big one. This, even using sort of a Tesla style electric motor, which are, good electric motors for cars, it would be way, way too heavy. Like the weight of electric motors. I've described this thing where all right, we had the turbine engine and we had the separate propulsive engine and we coupled them electrically. The weight of those electric motors and generators attaching those two things would weigh more than the airplane itself with old style motors. So we've seen a Tesla, I just have to use numbers in this. A Tesla style motor is roughly 2 kilowatts per kilogram. Just note this is a number. The number is 2. So if we have 2,000 kilowatts or 2 megawatts, that's 1,000 kilograms of motor. That's really heavy. The engine that this is being attached to is 200 kilograms. So just the thing that the engine is attached to is 5 times as much in the old paradigm. What has changed is, in part, we had silicon carbide semiconductors. This allowed really high voltage, higher efficiency inverters that drove down motor weight. And then the other thing is just we just got much better at making electric motors. We actually get our motors right now from a Formula One vendor, where it sort of cost us no object. Let's make this as power dense as we can. And our low performance motors are about 5 times better on power density than like a Tesla motor. I'm sure they're also immensely more expensive, but for aerospace, it's all cheaper than jet engines. And then we've got one more still, which is up to 27 kilowatts per kilogram. So we went from 2, then 10. Our current ones are 10, and we're getting other ones that are 27. So yeah, it's is it like a 14x improvement? That having a 14x reduction in weight is a really big deal for something, like this. Like that's why you can consider this. There's sort of like, there's like a mass, we had to pay a certain mass debt to this. And, the higher efficiency that we get from this thing allows us to pay that off very quickly. Like before, it'd be like, you could never pay off the sort of mass debt that you took on. Even if it was more efficient, the thing was too heavy. But now we're at the point where like, yeah, it's a little bit heavier, but you save that after like not even an hour of flying time. So hopefully that's makes sense.
I like the term mass debt that you use. I don't know if I've heard that before because, I think most things in aerospace engineering, in aerodynamics, is a series of trade-offs, right? I mean, you can simplify it all down to like 4 forces that are, all kind of acting against each other. And so I think the concept of paying off that mass debt is a really great way to look at it. And part of the paradigm shift of what you guys are doing with this engine is almost changing that formula in a way, right? Where you can kind of get that efficiency, maybe without the same trade-offs that existing options would have to give up. Talk broadly about kind of what the future of air travel, of, aerospace, of airplanes could look like 10, 20 years down the line if Astro Mechanica, engines and systems are integrated in everything.
Yeah, I'm realizing I'm falling into the trap of like, we started with the engine, but our main work, this was a prerequisite to what we're doing. I build airplanes. I'm actually not a propulsion person by background. It's like I was just working on this to make a better airplane initially. There's a second thing here, which is we're not burning jet fuel. I mean, we can, but we're actually using a much more cost-effective fuel. So the world that we're going for is this engine enables efficient supersonic flight. So sort of the big deal here was that bought us, it's a reduction, big reduction in fuel burn, but more than that gets its range. So back to sort of this mass debt sort of problem. Old supersonics couldn't actually fly that far because they were so inefficient that they had to carry all this fuel, and then you have no room for passengers. So you couldn't cross the Pacific nonstop on any sort of prior supersonic, to say nothing of the immense cost trying to run something like that. So the deal here of where we're getting to is we're going to be able to do supersonic flights, anything that a subsonic airplane can do. We can do it at least 3 times faster and at cost parity with not like business class fares. We actually can get to the point where it is like fully cheaper than existing subsonic airliners. So that is the world that we're going for. Another thing on top of this is I think that we'll actually do that. We're revaluing like this whole system. And so we're not going to do this even at airline size aircraft. Rather, we could, but the first plane that we're making more as like a DoD demonstrator. It's going to be a 20,000 pound aircraft. If you could put people in it, I intend to as soon as I can. You do 5 people, 5 passengers, like 2 pilots up front, 5 passengers in the back, and it would be probably on the order of a $3,000 cost per flight across Pacific for a private jet, a private jet from SF to Tokyo. You'd be around now that's, I should say, maybe we shouldn't talk these numbers publicly. That's going to be like what I think our operator cost could be. And again, that's like this is our first version of this. As you start to, and there's a lot more optimizations that can be had over time, but you sort of flip things in their head. Rather than selling a seat on an airplane, we change this to, well, you're just booking an entire jet. Sort of like we're in a situation where what we want to make is more like an Uber of the skies, and it's supersonic. But to do that, like imagine making Uber before you had cars. If there's like only buses and trains around, like you can't really do that. So you first have to make the car, and then you have to make sort of the network. And like this is a 20-year plan, that I'm going for on this. But we have lots of businesses that we can do, lots of markets that we can serve in the meantime. But that is the long-term goal of like replace airline travel with low-cost, supersonic, on-demand flight.
It totally radically changes, I think, like the operating model of the aircraft, but there still is this upfront cost to building these systems. And you reach some sort of economy of scale at some point. If you're building enough, you're operating enough, and it gets levelized across those operations. But, are you able to build, is the goal to build the aircraft itself?
Yes.
Cheaper upfront as well?
Yeah. I think there's an interesting sort of paradigm to consider on this. Like when you're doing a genuinely new thing, vertical integration is the way to go. I think there's these natural cycles. When you're reinventing an industry, you have to be vertically integrated, and like the more vertically integrated you are, generally the better. Over time, I can see this. Then you want to instead of horizontally, integrate, start to like have others sort of specialize. But like when you have to figure out a lot of new things for such a new operating paradigm, we will do everything from the aircraft through the operation, because it is just so dramatically different. Now, over time, again, I could see this like in 50 years, who knows what the path on that would be, but maybe that starts to get disaggregated again. But yeah, I think it's the natural cycle. But and for the company itself, part of how you also do this is like you do sort of always the Tesla model for something like this. Start with the Roadster, then the Model S, then the Model 3, then the Model E. That's, I think that's the way to do it.
Well, okay. So let's stay with that analogy, because I think it's a good one and something that people can resonate with to the extent you can share. I mean, what is, in your mind, is this kind of 5-7-seater, the Roadster? And then what's the Model S? What's the Model 3? What's the Model Y of Astro Mechanica?
Yeah. The first one, this one is like, so it'll be a Roadster for sure on this initial one. While I'm aiming for having it being something that we can quickly convert to sort of the civil market. I guess I should say the first aircraft just needs to work and serve sort of DoD functions. Like DoD is very different from civil. There's not a passenger certification. Like I would say it's somewhere on the order of, to make an airplane is some hundreds of millions. To certify it is well into the billions. And so this is like the gap of, all right, you just made the thing work versus, it will never fail ever. That's what you have to do on the passenger end. So the market that you start out with is like, well, DoD is much more concerned with initial functionality. Like there's at least as we're talking about it, not going to be people on board. So you start with that, and that's like you're good. It's a niche. I think it's actually kind of funny to suggest like the market for DoD is nowhere near as big as sort of consumer civil market, but much lower barrier to entry. It's more tightly coupled to just technical execution. Then we go to like, it's the same aircraft, but now we're going to make it our sort of next step down, kind of our Model S. We're turning our Roadster into our Model S. Might start to confuse analogies here, but we'll certify it. Some billions of dollars, but like the nice thing on that is like, well, we've been making, the idea here is you sort of start your financial engine. We've been making money selling and serving the DoD. I think there's like other sort of, maybe we can do, autonomous supersonic cargo or something like that as well. I don't know. So you go for these markets, you need to, first thing is like get your financial engine going. And then you can funnel it into later certification. So yeah, we go private jet is the 5-passenger private jet. I guess it'd be our Model S. Our Model 3 is probably going to be a 30-passenger, kind of like Jet Suite X. Go for something like that. And then eventually you'd have, sort of your Model E equivalent, where we'll finally, I will reluctantly, but finally we'll do a very large aircraft for the major city pairs. Because like the on-demand jet thing, while extremely cool, sometimes you just need planes running from like SF to New York or SF to Tokyo. Like those, there are a lot of people that are going to be going on those every day, and you don't have to keep it at this small size. But it's so much more expensive to make a big plane. Just like it's more expensive to make a cheap car than an expensive one. You do that last.
Okay, curiosity kind of got the best of me here, but I did a dive into the process of certifying airplanes and kind of how the FAA goes through that process, the Federal Aviation Administration. So, the type certification process is the primary method for approving new aircraft designs, and it typically has about 4 stages. The first stage is technical overview and certification basis. So the aircraft manufacturer presents the project to the certifying authority. In the US, that's the FAA, and in Europe, that's the EASA. A certification team is established, and a set of rules that will apply to the specific aircraft type is also determined. The next step is the certification program. So the manufacturer and certifying authority agree on how compliance with each requirement will be demonstrated, and the level of regulatory involvement is proposed and agreed upon. And then the third is the compliance demonstration. So the manufacturer demonstrates compliance with regulatory requirements through analysis, ground tests, and flight tests. So this is like the, demonstration, literally the demonstration and testing phase. This covers all elements of the aircraft, including airframe, systems, engines, quality of flying, and performance. And the certifying authority reviews documentation and witness tests. And then the last stage is technical closure and type certification issue. So once satisfied with the compliance demonstration, the certifying authority closes the investigation, and a type certificate is issued for the aircraft design. So some sort of notes to get across with this, right? Like Ian had said that this process can get into the billions of dollars for a company, right? But he didn't really talk about duration. So the certification process can take many years. So for example, the Boeing 737 MAX certification took almost 5 years. There's a lot of regulatory oversight, so the certifying authority, which is most likely the FAA, remains directly involved with testing. There's delegations, so some certification tasks may be delegated to qualified individuals or organizations, such as the Organization Designation Authorization, or ODA. But this is done under strict FAA oversight. There's comprehensive reviews, and there's international cooperation too. So there's often collaboration between civil aviation authorities for approval of aircraft for import into different countries. And so, it's quite a lengthy process here, but definitely one that needs to be done. So it'll be interesting to see how, Astro Mechanica's technology would fit into this in the future. But okay, just wanted to add that, and let's get right back in.
Got it. And you touched on something there that was my next question of, it's such a radical shift that I imagine new quote unquote markets open up with what you guys are doing. I mean, obviously this on-demand kind of smaller jet travel is like radically different than what we experience today. But when I think people think about air travel, they think about moving people with commercial airliners. They think maybe about fighter jets or DoD applications. Supersonic, autonomous cargo. I mean, what are some things that like open up with what you guys are doing? Because it's a totally different business model, economic model. The unit economics are different. Do you guys think about that?
Yeah. Well, I mean, I would say that one, the main one we talked about was definitely the private, like getting private jets to be, let alone supersonic ones, to be cheaper than like first class or business class fare. That's just such a reinvention of everything that like I think that is going to be the big one. There's some other pretty interesting ones on this of like we can go into all the ways that it can sort of change DoD as well. Like anywhere on Earth, large amounts of mass can cheaply be delivered anywhere on Earth in single digit hours. Like there won't be, as I've looked at this, like there will not be anywhere on Earth that crosses like probably the 7 or 8 hour threshold. It could be like antipodal flights like London to Sydney. So you start to consider like what changes sort of downstream from that. Another one of this is space launch. I initially was talking about this a lot more because we've had our DoD traction. We've moved away from like, we don't have to start there. I originally thought we did, but if you can very efficiently go to high speeds, you can effectively replace the first stage of a rocket. Like when you see a rocket, it's actually, 2 rockets, 2 stage. that lower rocket, like on Starship, that was going up to, somewhere around like Mach 5. And I think it staged somewhere around like 60 kilometers altitude. That's more or less that's like within range of what an airplane can do. So that ends up being this is to say, if you were to use a plane with our propulsion system, we can reduce the rocket mass needed to get any payload in orbit about 4x. So this was my original big interest. Like, you could take a Rocket Lab Electron. We don't even have to make the rocket. We could grab a Rocket Lab Electron, and right now it does 200 to 300 kilograms depending on the orbit, and you could 4x that. So it's a fairly big deal on that one.
And you brought up a good point there, I think, on just delivery is probably too weak of a word, but it's the rapid launch and the rapid response, and this concept of being able to bring mass to different theaters, different locations is becoming a bigger priority for the DoD. And we've seen it with, there's companies out there trying to store mass in orbit and have it be able to come back down to Earth. Or it's, do you put something in Starship and then figure out a way to, land a container? Are you guys going to kind of be in that market, and where do you fit kind of in that realm?
Yeah, I mean, this one, again, we found, like, over time, why not do everything? But yeah, this isn't something in the near term where we're, we'll see. I guess back to there's an early question of like customer feedback and interest. Like, if this is a thing that DoD really finds meaningful, like, happy to make and supply the planes for this. The one that we've heard that was like very surprising, Dark was bringing this up, was the concept of a sprint tanker. So it's kind of an amusing thing. Like, if you can deliver a lot of mass anywhere fairly quickly, we will be making a thing far faster than the fighter jets that are currently out there. So if you've got, pilots in some combat zone, you could get fuel to them. Like, rather than having a fuel tanker pre-positioned in some, potentially problematic area, like, you could actually catch up to the fighter jet, refuel it, and have it, like, get out of there. You don't have to have a pilot ditch over the ocean or something like that. Like, that's just like, I guess I heard there's a good expression of this. It's like, from a military perspective, it's like, experts talk logistics. And this changes the sort of logistical landscape so much that, when you can skip, like, we have all these like forward staging grounds, Guam and things like that. It's like, well, you can actually operate out of North America. Like, when you can just cross the entire Pacific, when you can do San Francisco to Taiwan in less time than it takes for a boat to cross the Taiwan Strait, you have this sort of interesting, like, well, we can, like, you don't need to have all these bases nearby, which can initially be sort of vulnerable. It's like, it doesn't even matter. Like, North America can just reach out to anywhere at that point. So yeah, this is going down some of the ways that this can affect.
I'm glad you brought up the point of logistics. We won't dive into it too deeply, but it is contested logistics, and also just thinking about logistics for the DoD and for anything is so important. And I think, years ago when I started diving into that concept, you think we're so technologically advanced that it's like, oh yeah, we could pretty much access most places on Earth relatively quickly. But that's not really the case, right? I mean, we are constrained by land and the range of the aircraft that we can move, or it's, we're constrained by the speed and the range of the boats that we have to move somewhere. No. I think you were gonna touch on that exact point. I mean, so any way that you can change how that operates, and if it's catching up to a fighter jet and refueling it in midair, and you can essentially double or even like triple the range of that jet or of that tanker or of that, aircraft, it changes how prepared we are and changes kind of response times and effectiveness on a totally different scale.
Yeah, and being able to do this at a smaller size is another interesting one. It's like sort of moving from mainframe computers to like personal computers, getting more granular like that. Doing that now with air travel, I think will really also change, or just, flight in general. It's like, there's certain places that you want to go to and like, there's just no direct flight. And so it becomes like extremely, even if the distance isn't that large, you want to get more granular with sort of your like travel unit. So this goes into like travel theory. There's a huge amount of friction sort of each changeover. So if you can cut down on those, I mean, this is the initial this is why people like private jets, for instance, like you're eliminating it is just like going to where you want to go. And so, yeah, if you're going to somewhere that's just like, it's near, say you're going like here to Thailand, but like, I know Thailand is a big country. There's a big difference of like, you do want to go to the north of it or the south of it. Maybe that was like another, 6 hours or something on the ground, or actually maybe like a full day. And it's like, this changes things where you just will appear where you want to go because you've got these like on-demand smaller aircraft that can literally go to anywhere. Like that is just the point to point, like at a like not even just like vaguely across Earth point to point, but like literally you're going to end up with some few miles of anywhere you want to be on Earth in hours. Like that's just not how things work, right? Like that is a wild way to exist.
It's a wild way to exist. And I'm going to throw a question at you. And this is like such a small problem in the grand scheme of what you guys are trying to do. But imagining a world where we have this on-demand, smaller air travel that gets you point to point, right? It totally changes the like hub and spoke model, of course, because you're getting your own jet. You're a pilot, you're a mechanical engineer, and like we both nerd out about this stuff. So I know you've thought about it. I mean, how do you think about dealing with the headaches that come with that? Because now you no longer can like have these highly efficient airports, these hubs, which maybe is a worse consumer experience. But there's some safety and there's some efficiency to that. But now it's like point to all these regional airports, smaller, landing strips, whatever it may be. Have you thought about that? Just a thought experiment, and that's not a near-term thing. But
this makes things easier. I mean, ideally, what you want like the fact that everyone is going from like San Francisco to New York for something like that. That's actually much harder because you're having all the planes try to go to the same place. But there's many more. So in the U.S., there's 500 commercially serviced airports currently, but we've got over 5,000 airports with a mile-long runway, and then like total airports in the U.S. is around like 20,000. But of varying lengths and so on. So we'd say like there's about 10 times more airports around than we currently service. And so you can actually just spread the load a lot more on that. Like that helps a bunch. So that's a big deal. And there is that now you want, this is kind of to this airplane sizing thing. You also want the planes to sort of like fractally represent those different scales. So like make bigger planes for the more popular, bigger city pairs. But for these ones where you want to be a little more like niche destinations and so on the point to point, like those are smaller planes, but definitionally like there's a lower population, fewer people are probably going to be going between these places. Like the planes can sort of correctly match. But it still is. I mean, so an interesting thing, like there's many fewer airplanes in the world than people think. I think the most I don't know if it's United or Delta. Like I don't think there's any airline with more than 1,000 airplanes. And the total number of airplanes, I've seen the numbers. It's anywhere from like 30 to 45,000 airplanes total, all airplanes. It's not that many airplanes. Yeah. So yeah, it's not like cars where it's like, yeah, you have that many cars in a single city. So yeah, there's definitely, I don't know what the sort of like scaling challenges are going to be there. I look forward to having this problem.
We will have done well. We will have done well. That is
when this is the issue we're having, like, yeah, very happy. Mission accomplished.
Exactly right. And then I'm going to bring it back to almost a question that I could have asked first, but your background, pilot, full stack mechanical engineer, kind of self-proclaimed, like truly full stack from like nuts to bolts to the actual selling. What was the aha moment for you? So I got the why now of it's the motors, there's some other tailwinds here. But when were you'd run other companies before, when were you like, I'm going to start this thing and I'm going to just change how aircrafts are built and operated?
Okay, we'll give Ian back the mic and let him answer the question right after this. We'll be right back.
Do you have a venture capital portfolio of cutting-edge startups? Without one, you could be missing out on enormous value creation and a more diversified personal portfolio. Alumni Ventures, ranked a top 20 VC firm by CB Insights, is the leading VC firm for individual investors. Believe in investing in innovation? Visit av.vc/foundation to get started.
Yeah, I mean, I started from like at a really young age. Before building real airplanes, I built experimental or model aircraft. And I was like 13 or so, started with that. And I think it was really obvious for us back then. So this is like 2003 in my case. We were the first to see lithium batteries, electric motors. Like we were switching from like these little like nitro fueled gas burning things that were total pain in the ass to like the electric stuff. And you're like, oh, this is just obviously so much better. Then and just like so like when Teslas and things like that came out, I was like, well, duh, this is like way better. So knowing that was the thing to apply to aircraft, I always like that was always in the back of my mind. But one of the problems, of course, is batteries were never like they could get 10 times better and they still wouldn't be nearly as good as burning a fuel. And because I like to fly far, everybody likes flying for different reasons. And mine is like I like going on like long distance missions. So I like heavy IFR. I like a good challenge. It's just way more interesting. It's like boring to just go putt around locally. So yeah, and I'd done well enough on sort of my flying career. Like I was up flying myself around in jets. And when I got to that place, I think that's really annoying again, like jet world is they're really, unsurprisingly, they're very expensive. And the reason they're expensive, when you start paying these bills and seeing everything is like, it's not just fuel is actually one of the cheapest things on a private jet. I wish it was just fuel. No, it's like fixing the things. They are insanely expensive. And this went into this whole world of like, for private jets, they don't make that many of them. There's not that many people that can dump millions or tens of millions in airplanes. And so the volume is low. Like private jets are not small airliners. They're not built that way. So they're not very cost effective to, there's no economies of scale to make them cheaper to build things. So what I realized though was there was a way to use electric. If you made everything on these aircraft electric, they would be far cheaper and simpler to fix. So this was like the genesis of everything. So it took a while to get there, but like if you do, including propulsion, if instead of having like bleed air and hydraulics and like low voltage electrical, have one system, highly redundant, but a high voltage electrical system, and then everything on the plane is that. That is a cheaper plane to fix. We saw a little bit of this. Boeing did this with the 787. They have like the cabin is not pressurized from bleed air from the engines. They actually just have 1.5 megawatts of electrical power, which is a ton that's just to run the systems on the plane. Yeah. And everything is done electrically. So it started with that. All right. This now puts us, and I was, we're working with like Honeywell on a potential hybrid system to make this like initially subsonic private jet that was very affordable to operate. We could already get to that place where we could compete with airline economics with a private jet. But then I had this sort of insight. I was actually going out fundraising for the first time, and this actually came about in a sense from like not, unsurprisingly, maybe investors weren't too excited to fund this. They're like, this seems really scary, FAA certification and so on. And was in getting turned down on that a lot. That I was like, you know what, screw it. I want to make a plane with this hybrid thing, and I have my own business. Like, I'm just going to go build this hybrid plane for myself using this architecture. But if I'm going to make it for me, this is what leads to the insight. What I want as a pilot is very different from like what someone would want as a private jet experience. I sit in the cockpit. I don't care I want a small, fast, nimble, aerobatic airplane. Just say like, ideally, I want a cheap to run fighter jet for me to putt around in, which is very different from the typical private jet experience. So, but to do that, using this hybrid, I wanted to use the hybrid architecture, but for something that's more fighter jet-esque, you want to use a fan as opposed to propeller. Propellers are obviously just less cool than integrated fans. But the problem is you have less thrust if you use a fan over prop. So I started thinking, it's like, well, what if I burn fuel behind the fan? Like, that seems a little weird. But like, I don't know, why couldn't you? Like, so I started thinking, like, why couldn't you do that? And I started, looking at like the thermodynamics of this and like, this is weird. This actually can work extremely well.
Can do this, yeah.
I hired an outside thermodynamicist as well. It's like, is this right? Can you also build a model on this? And like, does this actually? And like, yeah, it turns out that burning, like this whole sort of cycle efficiency is actually much higher. So yes, it came from the very silly like interest of like, I just wanted a thing that looked a little cooler. It could be fun for an aerobatic system. And like, that was, I sort of stumbled into this. And yeah, then it was like, this like sort of changes everything of like, this is dramatically more efficient. It's like what I was doing before, but now supersonic. And there's one more big insight, since I was looking at space launch things, and I like the idea of doing space planes. Rockets are not using jet fuel. They're all switching to methalox, which is liquid methane and oxygen. And I was pricing this out. And I was like, this doesn't seem right. LNG is a tenth the price of jet fuel. So it's more energy per unit weight. It's 50 megajoules versus 42 per kilogram. It's much cleaner burning because it's a simpler hydrocarbon and just dramatically cheaper. It's also 30% less CO2. So it's actually also cleaner. Like everything about it is better. It does, other than it takes up a little bit more space and it is cryogenic. If you design it for those things from the start, it's actually not that big of a deal. But I think one should just make airplane. Like that's just a thing that should just be done. Period. Make planes that run on LNG. So that was the next big thing of the low cost fuel. And you're like, holy shit, that's like this really makes sense now. So those two things together is just like a 1-2 punch. So yes,
it's a great story, and I think it just showcases the one, taking a very first principles approach to design, and two, just the benefit of having experience and knowing about all these other different worlds, right? Where like if you're at a larger aerospace company right now, like you may be very siloed into one area of how do we make X component more efficient, or how do we make X component a little bit cheaper. It stumbled into it a little bit, but you took a very different perspective, which I think has led you to where you are today.
Yeah, I think this is the vertical integration thing of like, there are so many, at the end of the day, what you want to do is you're optimizing for like the end output. And that doesn't necessarily, there are trade-offs within any given like complex system, like aircraft are complex systems. And so there's lots of instances where like, yes, it's okay that this one component got worse because it had some other attribute that like across the whole system was much better. So that is, and you need that kind of back to like when you want to do something radically new, this is why it works so much better to be vertically integrated. It's like, yes, there's just trade-offs that we can make across the spectrum that you're just not able to when you only have your one little siloed thing that you get to tweak. Now, once it sort of recrystallizes, again, I think this is the natural cycle of things. In some decades, it's going to go back to like, okay, we've kind of figured it out. We don't need this sort of flexibility across the full spectrum. And maybe it goes back to that. But for new things to happen, I mean, Tesla and SpaceX are the best examples of this. You want to be vertically integrated. You want to control everything. And yeah, then you can do things. You have a flexibility and agility that you wouldn't in the old paradigm.
And cost at some point. But I think to your point, it's the flexibility, the agility, how quickly you can iterate. It just totally speeds up those timelines. Yeah. Well, great. For all the listeners who are now very excited and big supporters like we are in Astro Mechanica, what's kind of on the horizon? What can people be looking out for? Is it like, prototype? What's kind of the next big announcement for you guys that people should be setting their alerts for?
Yeah, so late October we'll be debuting we've got a big event. I believe some AV folks will be stopping by. Wow. We've got our event. We're going to be demoing our first flight. It's like the full performance engine of what is going to power our initial aircraft. Like this is showing the full operating regime and efficiency, and like, yes, this is the thing working this way can power the plane. So that's going to be late October. Then, next up after that is we can finally stop just being thought of as an engine company, and we will go into we're making the airplane. So, yeah, that's going to be some single digit, like few years. I want to fly in this airplane, so I'm going as quick as I can on this. Get to flight as quick as possible and go for our Trans-Pacific demo.
Well, that's a good personal motivator. And there's some story at some point in here where it's like you will be the one that flies the first one off the the first piloted one off the assembly line.
Yes,
which will be
Yeah, that's the perk of starting. We're actually going to be the first to probably do like autonomous flight testing for a manned aircraft. So I can feel a lot more comfortable getting in the first one because it actually flew a bunch more without humans. And I definitely my joy of aviation, and I've done test pilot things before. I will be flying that. So
I love it. Well, Ian, thank you so much for taking the time. I had a blast, and we could probably spend a couple more hours talking about this stuff. So appreciate it. We're excited to be on board and rooting for you going forward.
Awesome. That was great chatting.
Awesome.
Yeah.
Thanks again for tuning into the Tech Optimist. If you enjoyed this episode, we'd really appreciate it if you'd give us a rating on whichever podcast app you're using, and remember to subscribe to keep up with each episode. The Tech Optimist welcomes any questions, comments, or segment suggestions. So please email us at info@techoptimist.vc with any of those, and be sure to visit our website at av.vc. As always, keep building.